Okay, so we did a train leaves the station, or two trains leave the station problem last video. In this video, I mean, I could have trains, like I said, planes, cars, people walking. But let's just say we had two airplanes, and one is leaving San Diego, and say this plane is flying at 400 miles an hour, and it leaves at 12 p.m. And a plane leaves New York City, and this plane leaves, let's say, at 3 p.m. and it's traveling 500 miles per hour. I suppose the obvious question is where will they cross paths and what time will that be when they cross paths? Again, when I think of problems that deal with velocity, distance, and time, I always write down the definition of velocity, which is distance divided by time. Even if I don't know where that's taking me, I write that down. Again, like I said in the last video, I tend to solve this for D and use this equation only because for most people it's a bit easier to use. Now, what skill do you have to solve most word problems, two equations and two unknowns? That said, there are always really, or I suppose you could break it down into two parts, word problems that is. One is where you have the words and you have to translate them into equations. And then the next part is where you solve the equations. In general, um, this is all relative, okay? It's not when I say easy or difficult, it's relative to each other. Generally speaking, this is easy and this is difficult. I don't have and there doesn't exist an all-purpose method to turn words into equations. It just doesn't exist. And there can be some small amount of ingenuity or cleverness, if there is such a word. You have to be clever in getting the words into equations. I mean, once you do one very specific problem, yeah, okay, so you know how to do that very specific problem, but there actually are an infinite number of word problems. So you would have to have a list which was infinite, which if you take some more advanced math classes, you'll find out you certainly could have. But for right now, or for most practical purposes, that doesn't seem very practical. Now, how on earth am I going to solve this problem? Well, let me just ask you a really seeming unrelated question here. Suppose this has a length of 10 and I chop off a length of 3. How much is left over? Now just think about this for a minute. A length of 10, chop off a length of 3. I think almost everybody's going to say 7. You know, no problems, no issue. Probably felt like you didn't even have to think about it. Suppose this was a length of 20 and you chop off a length of 4. How much would you have left over? And I think most people would say 16 without really giving it too much thought. Well, suppose this is a length of L and I chop off a length of X. How do I want to represent with symbols the leftover? So if you use these examples, I mean, where on earth did you get 7? You probably thought, well, it just seemed obvious to me. Well, what if someone said, I don't get it or I don't understand it? How did you get 7? You know, you might think about it for a minute and go, okay, 10 minus 3 is 7. Look, 20 minus 4 is 16. So how would we get this leftover here? It would be L minus X. Now, if I had started off with this picture here, if I just said, look, this is L, this is X, this is L minus X, you might get it, you might not. I don't know. Some people would, some people wouldn't, but it sure might seem like, I don't know, I'm doing some kind of serious mathematics. But when you look at this and this, you see, no, 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 this is really, really simple. Now, we're going to use this in solving this problem. So, sort of store this away in your mind for a second. There's one other thing I need to tell you before we can do this problem, or you need to know. or you need to look up, and that is the distance between San Diego and New York. Just for the purposes of this problem only, let's just say it's 3,000 miles. Well, it's probably a little bit less, but hey, that's close enough. So 3,000 miles between San Diego and New York. Um, I want to modify this drawing a little bit. There's San Diego, there's New York. And I don't know where they're going to meet. They're going to meet somewhere. Look, it's a real quick estimation. At 400 miles an hour, you know, if you fly for 10 hours, you go 4,000 miles. If you flew for 5 hours, you'd only go 2,000 miles. So it's going to take this plane more than 5 hours. And what that means is that plane will have left. And what that means is they will cross paths somewhere in between San Diego and New York City. So there's no chance of this plane getting to New York City before the plane in New York City leaves for San Diego. So let's just say they meet here. And I don't even know, you know, is it more than halfway or not? We don't know right now. Let's call this distance from here to here x. I'll call it d for distance. How do I want to represent this? Well, I don't know this distance from New York City to where the planes cross paths, but I'd rather not introduce a new variable. I could call it y or a or, you know, any letter you want, alpha. But instead, what the heck? Instead, let's call this 3,000 minus x. Now let's apply this equation. What's the distance the first plane flies? We don't know, x. What's its velocity? 400. How long will it be flying for? We don't know. What about the second moving object? How far will it have traveled? See, what's its distance? 3,000 minus x. What's its velocity? 500. How long will it have been flying? Well, not as long as the first plane because it left 3 hours later. So t minus 3. Okay? There's two equations and two unknowns. So in a way, what you do is you go take a nap, eat lunch, take a nap. You've turned the words into equations. At this point, you can actually forget about the words. Forget about it. Forget about the word problem. Just do the equations. So let's go ahead and do this. I'm going to do it by the substitution method. X is, the first equation is already solved for x, so we might as well start there. Let's substitute that in there. So 3,000 minus 400t. Let's go ahead and do the distributive rule. 500t minus 1,500. Let's get the t's on that side. That's your choice, of course. 900t. Let's add 1,500 to both sides. Yikes, 4,500. Let's divide both sides by 900. And look, I mean, this is coming out really nice. I didn't plan it to come out nice, but I guess I chose nice numbers. The fact that this is 5. Like I said, when you get a whole number for an answer, either you're extremely lucky or it was planned to come out this way. And I didn't plan this one to come out this way. So when I saw that it was coming out as 5, for a second I thought, am I making a mistake? It's extremely, I was going to say preposterous, but it's extremely unlikely that the answer would come out as a whole number. Okay, so t is 5. Put a 5 in for t here. 400 times 5 is what, 2,000? So x is 2,000. So the first plane will have traveled 2,000 miles in 5 hours, and that's where it will cross paths with the plane leaving from New York City. If the question was actually what time did they meet, well, this plane left at where to go. This plane left at 12 p.m. It flew for 5 hours, so it would be 5 p.m. Okay. The real question here is, how did I know to set it up like this? And the real honest answer is this. I'm not really sure anybody ever showed me this. I'm also sure that probably, you know, tens of millions of people have done it just like this. Somewhere along the way in doing mathematics and practicing enough, you just get the hang of doing this sort of thing. I know that's not what a lot of people want to hear, but that happens to be the reality. By struggling through word problems, some you get, some you don't get, after a while, you generally speaking get the hang of it. And they become more or less easy to do, at least, you know, this sort of word problem. But it takes practice, and it takes a lot of struggle and times where you can't get it. Um, I don't know what else to say except let's do the next kind of word problem. And this is completely different. And this is really, I guess, the infamous mixture type problem. So I'll give an example. Now you can mix all kinds of things together. You can mix coffee beans together. You can mix octane rated gasolines together. You can mix metals together to get an alloy. But let me give, I don't know, what example? Hey, I'll give the you've washed ashore on a deserted island example. So you've washed ashore on a deserted island. And what do people do? They wander around the island. They look for sources of food, shelter. Is anybody here? Can we get help? Is it really deserted? Maybe it's a peninsula and you're really attached to some country and you're not really lost. Okay, so people wander around. Oh my God, somebody's hurt, terribly injured. They're in agonizing pain. They're brought to you. And I forgot to tell you, you're a thoroughly trained healthcare practitioner of some sort. I don't know, you're an RN, you're a physician, PA. Person's in, they're writhing in agony, and you seem to remember, you recollect the best you can. Hey, I'm going to make up numbers right now, so whatever you do, don't do this in real life, because I don't know what the real numbers would be. But you seem to recall that what you want to give a person in this situation is 5 milliliters of a 30% morphine solution that would kill the pain without killing the patient. Now, it just so happens that when everybody was looking around this island, one thing they noticed, this appears to be an island where there used to be a coconut plantation, but it's long been since abandoned and no one's here. They found an old pharmacy. And in this pharmacy, they found more or less an unlimited supply of 90% morphine solution and 5% morphine solution. So you've got all the 90% morphine solution you could ever want and all the 5% morphine solution you could ever want. The obvious question is, how much of this should you mix with how much of this to get 5 milliliters of 30%? Now, this is a tough problem. Just no two ways about it. And if you look in 5 different books, they'll probably show you 5 different ways of doing it. Or if you ask 5 different people, they'll show you 5 different ways of doing it. I want to show you the easiest way. And I've actually had some teachers tell me, oh, you're making it too easy. Math is tough enough. We don't need to make it easier. Or sorry, we don't need to make it more difficult than it is. I can't make it easier that it can be made, but I have no need to make it more difficult. I'm going to write down a template right now. I'm going to write down really 2 equations. And I'm not going to justify them. Down the road, if you want me to, hey, we're going to start having Zoom meetings next week. Yay. If you want me to justify what I'm about to write down, I would absolutely love to do it. I used to do that for years, but it's a little bit complicated, takes a little bit of time, and I found that a lot of people didn't really follow it. So what I'm doing right now is I'm going to write down something, and it's just going to seem like a rabbit out of a hat. No explanation, no justification. I hate to say this, but for right now, I'm basically saying take my word for it, which is completely anti-scientific and anti-mathematical. But in the interest of not driving you crazy, here we go. And I'm going to explain what this means. Let me just write it down first. So a sub 1 plus a sub 2 equals a sub 3, and c sub 1, a sub 1 plus c sub 2, a sub 2 equals c sub 3, a sub 3. Once you have this, I'm going to show you mixture problems, piece of cake. It almost takes them from being the most difficult kind of problem to the easiest kind of problem, or at least very straightforward. Maybe it's like taking a long walk. I mean, it's not. I can't run a 4-minute mile, but I can walk 10 miles. It's not that walking 10 miles doesn't take effort. Maybe it takes a lot of effort, but I can do it. I can't run a 4-minute mile. And once I show you how to use this, you'll have no doubt that you can do mixture problems. Doesn't mean you're going to want to. It doesn't mean it's fun. There's still going to be a lot of effort. But you'll feel like, oh, I can do that. The A's stand for amount, and the C's stand for concentration. A sub 1 is the first amount of whatever you're dealing with. Could be gold. Like I said, could be coffee beans. That seems like a classic example. There's one in your textbook about coffee beans. There's one in your textbook about gold. It could be gasoline. It could be really anything you're mixing together. But this A sub 1 is the amount of the first thing you're mixing. A sub 2 is the amount of the second thing. A sub 3 is the amount once you get them mixed together. It's the total amount of the mixture. C sub 1, C sub 2, and C sub 3 stand for concentration. Also, in the next video, I'll show you an example where C sub 1, C sub 2, and C sub 3 stand for the cost of something, how much something costs. So I kind of like these letters. A, amount, that's easy to remember. C, cost. Do I expect you to remember this? No, not really. So there you have it. Just look it up, write it down. It's stuck in my mind because I've used it 150,000 times. I never sat down and tried to memorize this. What happened is I derived this, I figured this out on my own so many times that it just stuck in my mind. So how do we apply it to this problem? What's the amount of the first stuff that we're using? We don't know. What's the amount of the second stuff? We don't know. What's the amount of the mixture that we're supposed to get? The amount we're supposed to get is 5 milliliters. What's the concentration of the first stuff? 90. And I'm doing something right now which is a little bit of a high risk, and that is I should have a separate video, an aside video, a tangential video, and talk about percents because most people are not really clear about it. It's for most of the time I would say it's a somewhat risky proposition to use percents. It'd be better to turn this back into a number. 90% is 0.9 or 9/10. But let's just say this is an extremely forgiving formula or template here. It's two equations. It allows you for concentration to go ahead and just use 90. I could have used 0.9 or 9/10, and I'll get the same answer. So A sub 1 plus, what's the concentration of the second stuff? 5. What's the concentration of the mixture supposed to be? 30%. And the amount? 5. What you do at this point is, in a sense, you declare victory. It's two equations and two unknowns. Now we just become very robotic, very clockwork, very mechanical about the whole thing, and solve these two equations and two unknowns. So I'll go ahead and do that. But again, in a lot of ways, once you see this, you should say, oh yeah, I got it from here, no problems. Yeah. Okay, I was a little confused about the words, wasn't sure how to proceed, but now that we have two equations and two unknowns, it shouldn't really be an issue. So let's solve this for A sub 1. Hey, you don't like A sub 1 and A sub 2, use X and Y, A and B, U and V, alpha and beta, whatever you want to use. It's up to you. But I'll solve the first one for A sub 1, so 5 minus A sub 2. Let's substitute this into A sub 1 in the second one. And again, we're proceeding very mechanically. 30 times 5 is 150. Let's do the distributive rule. And you don't have to show all this work here, but this is negative 85, right? A sub 2. Let's subtract that from both sides. Let's subtract 150 from both sides. So 300 equals 85 A sub 2. Can we still see this on the board here? Yeah, so A sub 2 is, well, 300 divided by 85, and of course I want to reduce. I do notice that 5 goes to both of those. 5 goes in there 60. And how many times does 5 go in here? 17. So, and this would be what, milliliters. Again, I'm going to have, I should make a little note to myself here, but I won't forget it. I want to have a tangential or an aside video on percents and also on the metric system, and that'll be coming up pretty soon. Actually, I should do that in a day or so. There's A sub 2. Where's A sub 1? Right here. So A sub 1 is 5 minus 60 over 17. So A sub 1 is 25 over 17 milliliters. There's my answer. Of course, these two right here, if you add them up, 25/17 plus 60/17, you get 85/17, which reduces to 5, which is better because that's what you're supposed to have altogether. So I'm going to end the video now, but I'm going to do another mixture problem in the next video. The key thing is to know about this template. Wait a minute here. So whenever you're doing a problem that involves distance, velocity, and time, I think of this. Whenever I'm encountering a mixture problem, I go to this template right here. And for all the problems that we're going to see, this will solve mixture problems, any mixture problem. I'm going to do a couple others where the setup is a little bit different, and you'll see these in the book too. Chapter 4, I think it's 4.3, but I'll double check that. You can tell because this section is called mixture problems, so you can't miss it. All right, so hey, that's enough for this video.